The earlier we start, the quicker it will be the pain. So, well, first of all, I'd like to thank Sabine for the invitation. And she asked me to talk about black holes in colliders. So, if you are wondering why you have to sit here half an hour to listen to this, then it's certain. I'm just kidding. And the second thing is that I'm a black hole hunter. So, a black hole hunter is a white hole. So I will reflect, okay, any questions, okay, that you ask me, okay, and especially skeptical questions will be reflected in that direction. You see there with that guy. So. All right. Well, the LHC is finally working, sort of working. It's not running at the design energy yet, but as you can see here, this is a plot I got from the CERN website. The luminosity is ramping up, and now there are the LHC is running with energy per beam of 3.5 TeV, which is half the energy per beam of the the design sensitivity of the LHC. So finally, we have been waiting for a long time for the LHC to come online, and from now on we can start playing a little bit with the data and start testing ideas about physics at the TeV scale. And as you have heard in the past, and also this conference, there are a lot of theoretical ideas that we might be able to finally test. All right, so what are the most popular scenarios for physics at the TeV scale that the LHC might have chance of probing? Well, we have SUSY. SUSY is the most popular one, is what most physicists, at least those from the string theory side, they are hoping to see. And the SUSY is a well-developed theory, so it has quite precise predictions. So we know exactly what to expect from SUSY if we're going to see it. Then another popular class of models, and this was is pretty recent, so they came out about in the last 10, 50 years, is TeV gravity. So instead of observing SUSY at the LHC, what we could do is to observe strong gravity effects. And that's essentially the reason why I'm here today.
Or both.
Or both, okay. Let's keep things simpler. Simple. All right, I put here a third let's say bullet, with our string resonances. So there may be the possibility that if gravity becomes strong, so the TeV scale, actually the string mass is a TeV scale, so we could see string effects at the LHC. And then there are a plethora of other models under the others. So I'll try to focus a little bit on these, in particular in the central one. So please don't feel offended if your model is here under the others. There is a chance that nor SUSY TeV gravity string effects will appear at the LHC, so you may still have a chance if you are under the others. Okay, so let me focus a little bit on gravity at the TeV scale, and let me remind briefly what we hope to see, or what we could see at the LHC. So if TeV gravity is correct, so gravity becomes strong at the TeV scale, and if you have gravity in a strong regime, so what you can see are both perturbative and non-perturbative effects due to gravity. So mv is the Planck scale, the Planck mass in the dimensions. Of course, Okay, I'm disconnected now. It's okay. So if we are, if MD, if the Planck mass is about a TV, then if we approach the MD scale, then we can start seeing non-perturbative effects, of gravity. Examples. Well, we can start seeing a tower of Kaluza-Klein modes. We can start seeing graviton production, assuming that gravitons exist. Okay. Both virtual effects, so loop effects in particle interactions, or real graviton production. Also, as I said, if the string mass is at the TV scale, we could start seeing string resonances, so radio resonances due to strings. If we go to higher energy, so at energies above the Planck scale, now gravity is really the dominating force. Yes?
Yeah, so it's my understanding that from precise tests of the standard model, there are strong constraints on a whole bunch of things, like another generation, right-handed, W's disease, and so forth.
Mm-hmm.
So from precise tests of the standard model, do we already have constraints on these?
Yes, there are constraints on this scale. Of course, you can always push the scale up to these models.
Right, but are those constraints relevant to the LHC?
No.
So they are
yeah.
relevant to the LHC.
Yeah, they are around the TV, those constraints. But, when the LSC will run at the design sensitivity, will run with a center of mass of 14 TV.
Okay.
So
You're above those.
yeah. For example, there are constraints on these models coming from the D0 experiment, Fermilab, even the lab, but they are still low enough that it allows for this possibility. So I was saying non-perturbative effects. So if you go above the string scale, now this point gravity is really the dominating force, so it should take over. And no matter what theory of gravity or quantum gravity you have, it's reasonable to expect that any theory of gravity, quantum gravity, gravity in the strong regime, will include the possibility of black hole formations. Okay. So what we should expect in non-perturbative effects is, for example, the formation of black holes. All right, so let me spend a few words about the mechanism. So black hole, mini black hole formation in particle colliders at the TV scale was proposed in these two famous papers, seminal papers, about 10 years ago. And the author of one of them is there. So that's why I said all skeptical questions to him. So the idea is very simple. So you take two particles, and these two particles have a center of mass energy during collision above MD, above the Planck mass. So from now on, I'll assume that the Planck mass is 1 TeV, just for simplicity. So you take two particles, you make them scatter with a center of mass which is higher than the fundamental Planck scale, and with an impact parameter which is smaller than the inverse of this center of mass energy. Essentially, this measures the Schwarzschild radius which is associated with that energy. So what you are actually doing is taking a lot of energy and you concentrate it in a very, very small region of space-time. So this is essentially gravitational collapse. It's a very special kind of gravitational collapse. So it's a gravitational collapse that it's relativistic, so it starts with matter at relativistic velocities, and it's highly asymmetric. Okay, so it's something completely different. I mean, the boundary conditions are different from gravitational collapse that you have, for example, in astrophysics. Nevertheless, this is a gravitational collapse. And now there are numerical simulations, full numerical simulations of Einstein equations describing this gravitational collapse. So it's actually we know that this is actually going to happen. From the theoretical point of view, we know that if you scatter two particles with high enough center of mass energy and small enough impact parameter, you are going to form an event horizon. So, if this indeed happens and you have the formation of an event horizon, Hawking tells us that this black hole is stable and should decay by emitting Hawking radiation. And again, this is a leap of faith, so we have to believe that Hawking radiation exists and it behaves at these energies in these regimes as the theory says, as we know. Yes.
I have a question regarding this point, because something that always worried me. How do we know that we are well within, let's say, the semi-classical regime? Because this black hole is formed slightly above the TV scale, no?
Okay, it depends on the energy, indeed. The higher you go with the energy, the black hole becomes more and more classical.
Yeah.
So, if you want a quantitative measure of that, you should measure how many degrees of freedom the black hole has. So, for example, if this fundamental scale is 1 TeV, and you are forming a black hole with a mass which is 10 TeV, then you have already a high number of degrees of freedom that you hope you may treat the black hole as a classical object.
Okay. You estimate them with the area.
So
yeah. Yes.
Maybe you should specify that the construction we have, the early Venus construction, that actually goes back to Penrose, works in the limit where the mass of the black hole is infinitely bigger than the planet mass. Now, people have then shown that if you write a path integral for that process, that's what we believe in the semi-classical picture.
Mm-hmm.
That's what we know.
That's correct. That's correct. And I would add that we do what we can do, not what we would like to do.
However, the experiment is independent of the theory. So if there is a black hole, no matter at what regime you are, you should see spectacular.
Right.
jets.
There are some signatures that should be common, should be generic enough.
Sorry, but whether you're in the semi-classical regime or quantum regime, the signatures will be quite different.
Exactly, I was just the same.
Because the semi-classical black holes typically decay to many particle states, whereas the quantum one will decay to just
No, but I said the experiment should
Right.
tell you.
No, but the problem is that how you interpret the experiment.
That's
Okay.
different.
I have to say one thing.
The question is how do you recognize
Okay.
the pure of the decay of the cube without how you recognize the pure of the quantum black hole without decay, say, into 6 states.
Right. Instead of jets, yes.
Exactly.
All right.
If it is jets, my claim is, if it is jets, it will be semi-classical.
Let me give you some.
No, it's 6.
Let me just give you an example. So let's suppose that the Planck mass is 1 TeV, okay? And let's suppose we'll see that we also introduce another parameter, which is the minimum mass of the black hole, because the Planck mass could be 1 TeV, but you may start forming black holes only when they are 2 TeV of mass, okay? So there is this minimum mass. Now, even if you form a black hole at the LHC, which has a mass close to the Planck mass, okay, so it's quantum, we are not going to detect it because it will be in the junk of the LHC. So if we are yes, and I'll show you simulation. So if we are going to detect a black hole at the LHC, we are going to detect a spectacular black hole. So once that happens, once in a blue moon, okay, and it has a mass of 12 TeV, okay. In that case, I'm confident enough that we are already close to the semi-classical picture.
Martin, that's very conservative way of approaching this problem. In fact, precursors of black holes in string theory, in toy models, would decay pretty much like black holes. String balls, for example, which is a long jagged string which is wrapped around itself, would decay in a very similar way, except that it's a Hagedorn temperature, a Hawking temperature, which does not depend on the string ball mass. So you could distinguish one from the other by the dependence of the mass, of the temperature of the mass. And mass is not fixed because it's not a resonance; it's a state.
I like to be conservative because I heard these questions about quantum black holes all the time. Okay? So I would be happy if we see one spectacular black hole with a mass of 10 TeV. That would be enough.
So,
yes.
Is it possible to have a black hole of 10 TeV if even when the LHC is going to be at the maximum possible energy, each parton will have at most?
That's why I
2
said.
TeV, for example,
That's why I said that it happens once in a blue moon, but it will happen.
Once in a blue moon.
Yes. I didn't give you the rate, but
It's a patient man, but many of us would be happy with 5 TeV black hole, 3 TeV black hole.
yeah. If the LHC runs for 10 years and I see 10 black holes, one per year, I think it's okay. I don't need to see one black hole per second. Okay, so it should decay, and it should decay according to what Hawking says. And by decaying with Hawking radiation, it will emit particles that live on our brain, and it should be detectable. And if this is true, the decay signatures will be very distinctive, and we'll see what these decay signatures are. At the end, when this black hole shrinks and it becomes quantum, then we don't know what's happening. Okay, so it might go, it might leave a remnant, it might go off in a burst. We don't know what. So we have to be open for all these possibilities. Okay. But the signatures during the Hawking evaporation phase, those should be enough to determine if there is a black hole. All right. So what are these signatures? So a little bit of phenomenology. So usually the cross section is very large and it's steep, and it's pretty steep. So it grows much faster than perturbative cross sections of standard model of other processes. The black hole is supposed to be spherically symmetric, at least in our brain. So what happens is that it will emit Hawking radiation in essentially any direction. So this translates in a lot of transverse energy and in high sphericity events. There will be high multiplicity events. So if the yes.
Can I ask one question here which is related to theory? There are two kinds of string theories. One in which all matter of the standard model is confined on the brain.
Right.
And then there are the models that you engage particles, the universal extra dimensional models. Now,
yes.
There is a difference in the behavior of if the emitter matter is only in the standard model or is diluted in the bulk. So my question is,
right.
How could you tell? So because maybe the matter is diluted in the bulk.
Yes, there could be. I mean, we know so little that there are a few things that we have to hope for. Okay. So, for example, if there will be Kaluza-Klein modes, okay? So the black hole will emit also a lot of Kaluza-Klein modes. Now, if the black hole emits gravitons, emits gravitational waves, both at formation and during the evaporation phase. So one has to look at the real physics, and we don't know enough of the real physics. So it could well happen that a black hole forms, but 90% of its energy goes into the bulk, and so the only thing I should see is some missing energy. But then
it could be supersymmetry. That's what
right. But just with missing energy, my point.
Let me clarify here. She's talking particularly about ADD black holes. In ADD, all the standard model fields on the brain.
That's right.
Universal extra dimensions do not lower the Planck scale, so they won't help you to deduce black holes.
Oh, I see. You cannot have.
Right. The only model in which you could have bulk particles and still produce the black hole is Randall-Sandler, where you put fermions of the brain. But then, you still would see different species.
The cross sections are suppressed though because of the bulk wave function.
True. Right.
But even the ADD model, you have Kaluza-Klein modes, so that you expect that black hole would emit Kaluza-Klein modes. So. And even there are a lot of studies trying to determine.
There's only Kaluza-Klein modes of graviton in the ADD model.
Yeah, but they will go into the bulk as well.
True. Right.
Yeah. But even from the purely classical point of view, there are a lot of calculations to try to determine how much of the initial center of mass energy is, there is some inelasticity effect. So you expect some gravitational wave emission. As I said, this is a highly symmetric and relativistic collapse, so you expect a lot of gravitational emission. Anyway, so hopefully high multiplicity events, so this means a lot of hadronic jets coming out from the event. As far as the particles in the bulk are concerned, so we would expect more or less a ratio of hadrons to leptons of 5 to 1, and this is simply due to the fact that there are 5 more degrees of freedom in hadrons than in leptons in the standard model, but these two could change if you have other multiplets or other particles. Generally large missing energy, and you could see that at a certain point for processes with high enough energy, this process should take over all the others. Okay, so suppression of other perturbative events. Okay, uncertainties. A lot of uncertainties because we know really little of gravity in this regime and this kind of processes. So as I mentioned before, there could be a lot of energy loss in gravitational radiation and in elasticity. We don't know what is the minimum black hole mass formation. It might well be that you cannot form any black hole with mass less than 10 times the Planck mass, and then we will be almost toasted for the LHC. We expect the black holes to rotate the Kuiper coil. So, for example, we don't even know what is the emissivity of a rotating black hole in d dimensions. Okay, we don't know the gray body factors for all fields, in particular for the graviton fields, for d-dimensional rotating black holes. So these are all unknown that we have to take into account. We have never tested nor observed the Hawking phase. As I said, we don't know the gray body factors for all fields, and we don't know if there are quantum gravitational effects that are also relevant to this regime related to what we were discussing before. So keep in mind that I'm not here to tell you that in 1, 2, 3 years we'll see black holes at the LHC. I'm here to tell you that there may be this possibility. And since there is this possibility, it's worth investigating what we should see. Okay? But don't come back to me in 5 years and say, ha 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 ha, you gave a talk about black holes in collides, because I'm not claiming that this is what's going to happen. But since we have a chance of testing the theory, I think it's very interesting. Yes?
Are you willing to make some kind of statement if by 10 years from now or 10 years from now or after a certain amount of luminosity no such event is seen, then you put it down on something? Yes,
because I think one should not fall in love with the theoretical model that you are working on. Right. So this is a pretty generic idea, okay? So if the LHC does not see anything in 10 years, they are not forming.
Right, so then is there a parameter that you're bounding?
Well, yes, the Planck mass.
Well, no, because you don't know how to form quantum black holes, so you're
all
not
right.
adding anything.
You can always push up the Planck mass, okay? But all this TV gravity scenario was born with the idea to bring down the scale of gravity to the TV scale.
So if nothing is seen in any years, will somebody publish a paper that says the lower bound of the product of the dimensions in the Planck mass or something like that just adds up to 95% of sleep?
They will do it, but not from the black holes.
Not the black holes.
This will come from other observables. It is a much less speculative.
A few months.
Hey, I have a question. Very often when one considers something like this, the effect of virtual black holes would be possible to bound. Has anybody considered putting a bound on the contribution of the virtual black holes that must contribute in the loop?
How do you calculate it?
Sorry?
How do you calculate it? I mean, you just don't know how to calculate those things, so that's why people look at it.
But those would be
No, there's a long paper by Gordy Kane, which happens to be long.
Yeah, but anyway, I never understood that because those will be perturbative effects. So here we are talking about a non-perturbative regime. So I don't know what a virtual black hole is. So I remember one paper, but
yeah, the standard argument is that you could induce proton decay by virtual black holes, but that doesn't work. There's 10 different things you can do. It's not smooth.
okay. Let me just tell you a few words on the third bullet, string resonances, because I'm going to show you a couple of plots comparing black holes to string resonances. I'm not really an expert on this. All what I know, it's more or less contained here and a little bit more. The idea is very simple. So the idea is that you could have the string mass at the TD scale, and so in this case start seeing string resonances at that energy scale. And you can compute the cross sections of these string excitations. Essentially, they are Regge resonances. And you can do it at the tree level, so essentially just by computing the string disk cross-section for these events, so you expect them to be fairly independent from on the different moments. And these resonances could lead to processes like gluon-gluon going to a gluon photon that you don't have at tree level in the standard model, or in this case, oops, in this case, there could be a possibility of looking at string resonances. Okay? So I'm going to show you a little bit how this model, for example, could be distinguished from the black hole formation model. All right. So how do we tackle the problem to actually try to simulate a black hole formation at the LSC and compare it eventually with the data that will come out from the accelerator? So the first step is to build a generator for these events, and there are several generators on the market. Each of them claims to be the best, and each of them has problems. Not all the claims are actually factual in these generators, but more or less there are variations, but when you compare the output, you get more or less the same thing. Which is essentially due to the fact that we know so little about these processes that everything at the end boils down to a few significant observables. That's one. When you choose your favorite generator, you can simulate the events. You choose a benchmark, you do your run, you reconstruct the events according to the geometry of the LNC, and then you will compare them to the data by looking at some signatures that allow you to discriminate black holes from other models, for example, like SUS. And you do this comparison. So this is essentially what I'm going to show you briefly for a few of these models. So I choose the catfish generator simply because I wrote it, so I know what's in it. I know the crack is, I know now that it's working very well. And so you choose a generator and you generate your event. So these are a few of the characteristics of the generator. So the generator takes 2 protons, actually 2 partons. It samples them according to the parton distribution functions, computes the center mass energy of the collision. It includes the possibility of inelasticity, so you can take into account how much gravitational radiation is lost in the collision even before the black hole is formed. It creates the black hole, computes the cross-section, creates the black hole, and then it evaporates the black hole according to the emissivities of the various fields that that we know. I have to say that it works only for spherical symmetric black holes, because as I said before, we don't know the emissivities of all fields in the rotating case. And then it decays the black hole according to Hawking radiation until it reaches a minimum mass, a quantum mass. And at that point, you can decide to let the black hole rest there as a remnant, or go off in a certain number of hard quanta.
What is the size in numbers of your quantum mass and the actual mass of the
You get it's a free parameter in the generator, but essentially you put it on the order of the Planck mass.
Yeah.
Or
I mean the quantum mass is.
yes, the quantum.
And the black hole mass should be an order of magnitude higher.
The black hole mass is decided by the collision on
Yeah.
yes.
So
yeah.
10 TeV.
It can go from the Planck scale to 14 TeV.
Okay.
Yeah. It samples through the differential process. So charge and angular momentum momentum are conserved. The global symmetries are not. Yes.
Yeah. So a fraction of the beam energy goes into the partons, which then goes into the black hole.
Yes.
So how can you estimate missing mass if you don't know what the original energy of the length?
Indeed, the missing mass, the missing energy is not a good parameter to characterize these events. Yeah. Because anyway, yeah, I mean, looking at what you miss is never a good way of singularizing. There are yeah.
You can look at missing PT, so transfer.
Missing PT.
That's what you would see.
But missing PT, you have missing PT also in SUSY events. You have, yeah. So again, it's not.
Okay, but you had mentioned missing energy and one thing happens.
Right. Yeah, but it's not. Yeah, it's not. It's not a good way. And you can also allow for modification of the Hawking evaporation phase, so the black hole actually settles down automatically when it reaches the Planck scale. So you can introduce a minimum length parameter in the generator. Okay, you run the generator. This is what you get. Okay, so for example, this is truncated output for one event. So you have a bunch of particles with their momentum and their energy. Some of these particles, for example, these 3 hadrons here, they come from the hadronization of the proton remnants during the collision. Okay, only 2 partons going for the black hole. The rest of the protons is junk and will hadronize. Okay, and you see that they carry a lot of energy and they are essentially hadrons. And the transfer momentum, so px and py, it's very small. So they essentially go down the pipe. So I should not worry about that. Then I have particles that come directly from the black hole. Okay, for example, these 2 gravitons here, they simulate the amount of gravitational radiation which is emitted at formation. Why there are only 2, I don't see them. So the only thing that I use them for, I have to take into account a certain energy which is lost in gravitational radiation. Okay? So the simplest way of doing it is say there are 2 gravitons that carry away a certain amount of energy, a certain amount of... they are opposite, so they don't carry away any momentum. Okay? That's why there are only 2. I'm not going to observe gravity. So they are only here to represent the amount of energy which is lost in the collision.
And they're assumed to be back-to-back, essentially.
Back-to-back because I'm assuming the gravitational emission to be spherical. So that's why they are back-to-back. Then there are other particles here that come from the black hole. Actually, the black hole will emit quarks, will emit leptons, and if they are quarks, they will hadronize and produce pions, kaons, all sorts of other particles. How do I know that these come from the black hole? Because I look at the transfer energy, and the transfer energy is pretty high compared to particles that come from the beam remnants or from initial and final radiation. And then there is a bunch of particles that indeed are due to final state radiation, initial final radiation. So this is what I get, and then I can put it in the geometry of the detector of the LSC. This has been done by one of my colleagues at the University of Alabama. It's just a test. And you can reconstruct what you should see in the detector. I'm sorry you cannot see very well, but this is for CMS, and essentially you should see a lot of jets that come out transverse to the beam. All right, so how do I distinguish this scenario from other scenarios? I said before that just looking at missing PT or missing energy is not really the easiest way or the proper way. So I told you before that among the signatures of black holes, we have this high sphericity. So black holes will emit particles with a lot of transverse momentum. And so a possible way is to look at sphericity and the second Fox-Wolfram momentum of the collision, which is essentially a measure of sphericity. And in these plots, I compare, for example, the sphericity between SUSY, a typical SUSY event, these pink dots, with possible black hole scenarios. And let's just focus on this one, just for the sake of brevity. So this is higher the sphericity, higher this parameter, means that the event is more and more spherical. Okay, lower this value means that the event becomes planar. So SUSY events, since SUSY events have a well-defined chain of interactions, do not produce highly spherical events. But black holes, since particles are emitted essentially randomly in any directions, provided that you conserve the momentum, they can lead to events that have a lot of these transverse jets, so high sphericity. Now, what's important to notice here is the following, is that while there are cases, so this is a black hole for a Planck mass of 1 TeV, this black hole distribution for Planck mass equal to 2 TeV, this is the black hole distribution for Planck mass of 3 TeV. So, if the Planck mass is high enough, then you can discriminate the two pretty easily. And the reason is that the higher the Planck mass, the more massive is the black hole, the more quanta it will emit, the more spherical the event becomes. But if you look at the 1 TeV case, well, the discrimination is not so strong. So even just by looking at the sphericity of the event is not, I mean, it won't be the smoking gun. Yes?
Not to mention that most likely the black holes will be produced rotating.
Yes,
and then
yes.
In low TeV, the sphericity could also come from angular momentum.
Yeah, the angular momentum could play.
But the angular momentum is not very high.
Yes, no, I mean only...
It's figures of the order of 1.
Yeah.
So what's the possible way, it's not the only way, but a possible way to distinguish them? Well, it's to look at dilepton events, okay? If you have a SUSY process, eventually the SUSY process will end up with the lighter supersymmetric stable particle, okay, and a lepton, okay? So you can create in SUSY events that are dilepton events, so you have two leptons going off, and they are transverse with a high energy. But they are related. They are related because these leptons come from a unique chain. So you can reconstruct the invariant mass of these leptons and get a value. Okay? The leptons coming from the black hole are completely uncorrelated. Okay? So if you compute if you select events with two transverse leptons at high energy, and you reconstruct the invariant mass of the event, you get almost a flat distribution, because this lepton can go off in any direction, and essentially with any energy. So, if an experiment experimentalist selects the electron events, okay, at the LHC, and reconstruct the invariant mass, what they should get are two different curves according to if SUSY is, if these electrons come, for example, from a SUSY theory or from a black hole. Okay? So you see that the SUSY curve has essentially a cutoff at this point here, okay, of the GV, which is essentially the mass of the lighter supersymmetric particle. While you can have events of the electron events with a very high invariant mass, even of a few TeVs. So this would be a way of distinguishing the two. And you can repeat the same thing with other scenarios. So for example, one of my students did a study how to distinguish gravitons, Kaluza, Ronald-Sundrum gravitons and black holes. And again, if you look at the electron events, you would get a very clear signature. So for example, in this case, in this scenario, the Ronald-Sundrum scenario, the electron events come either from the decay of Z zeros. So when you reconstruct the invariant mass, you get a peak at 90 GeV. Or they come directly from the decay of the graviton, and in this scenario, the graviton has a mass around 1 TeV. So you should get another strong peak at 1 TeV. But you will never get invariant masses of the electrons at very high energy scale. Same for strings. I'm going a little bit quicker, but you got the main point. In the case of strings, what we are looking at is not the electron events, but we are looking at the gluon photon events. So essentially one reconstructs the invariant mass of these diphoton events, and again the game is the same. So this is a possible way to do, and electrons are usually give you a clear signature, much less messier than jets. So that's as I said, this is a possibility to distinguish in the two. Okay, conclusion. So we know that something must happen at the TeV scale. This could be gravity. This by no means sure, but it's a possibility. If this happens, it's quite reasonable to expect some sort of non-perturbative object forming in collisions. This could be string balls, this could be black holes, could be string resonances, and this should give a clear signature. On the other hand, if I don't see anything, going back to the question before, I can put constraints, and essentially put constraints on the Planck scale. So if I don't see anything and I keep raising my Planck scale to save the model, at a certain point I'll have to throw away the model, because these models were invented to bring the gravitational scale down to the TeV scale. If now I found that there are constraints that imply that the Planck scale has to be 100 TeV, then the whole construction has no purpose anymore. Okay? So even if I don't see anything, I can still learn something about the possibility of extra dimensions or the value of the Planck scale. And of course, you could have different kind of objects forming, like string resonance, brains, and so on, if this scenario is correct. So, and I think that's it. Thanks. Don't throw tomatoes or fruits at me.
So you choose.
Okay. Just only clementines. They are soft. Oh, I choose. Okay, let's go this way.
Okay, so I'm a little bit surprised that you've not mentioned non-thermal black holes. I mean, I think it's now well understood, or well appreciated, that the likelihood we produce semi-classical black holes at the Large Hadron Collider is very small, essentially because they're out of the reach. Now, people have realized that there's a good reason to extrapolate these semi-classical objects further into the quantum regime, where you get to non-thermal objects that would decay typically back to 2 particle or 3. Mm-hmm. Now, those are very interesting signatures that actually would be easy to see, like a jet and a lepton back-to-back, or E plus, mu minus. There's a lot of interesting phenomenology. You can classify all these non-thermal objects like quantum in terms of the quantum numbers of the quarks that created them. So that's something that
there is one of those 4 generators, QDA.
I know,
claims,
but it'd be good to cross-check those things. I think it's very important to include those events in the other generators because that's what we have a chance to see.
Yeah. Yeah, that's probably worth. We try to include several things in our generator, and then at a certain point you include all these things. You change the parameters. You hope to see an effect.
It's not just change the parameters; you change the physics,
yes,
right?
Yeah,
in a radical manner.
That's why I said that probably that's I would say the only thing that is worth trying to include.
But that's the thing to focus on, I think.
Yeah. I think that right now, we are at a stage that we should probably wait for the data.
But
and
for me, this need those simulations. I kept on being asked about those things. How good you can.
Right. Yeah.
So I think it's really important and will be rewarding.
Yeah.
Because that's the first thing you could see. With the data you're going to have by the end of the year, I think you can see some of those effects.
Yeah, that's good. Yeah. That's maybe worth doing.
But I'm a bit surprised that you say something like these are basically quantum objects, and you know that they came 2-3 passes. So how you can be so sure of what happens?
Okay, frankly speaking, you know nothing, but you can extrapolate from the top, semi-classical to the quantum regime. Then you would think that as you extrapolate to the quantum regime, your black hole becomes more non-thermal, and that means it decays to few particles. And then there's the other way to do the thing, which is the Veneziano and Maddy and Co. approach, which is to use some gravitons, and you start to see black hole precursors appearing, and that would correspond to also quantum black holes. So there's a good motivation on both sides for an object that is non-thermal, that would resemble strong scattering, essentially.
Non-thermality I could buy, but non-thermality I can buy, but it seems to me weird. I mean, I'm surprised that you can even predict what you're going to see at LHC in this.
Well, what you know
this deviation
is, then you don't know how they form, you don't know but you can, let me assume for a second they do exist. Then you know the quantum numbers because they form by quarks that carry charges, and from that, you could at principle probe the symmetries of quantum gravity, like whether...
Are you assuming conservation of quantum numbers?
The gauge charges, yes. You don't want to violate
at the Planck scale.
Gauge symmetries are sacred.
At the Planck scale?
Yeah.
Well, you can assume it.
So discrete symmetries can be violated as much as
you can assume whatever.
A gauge symmetry you don't want to violate.
It's the other way around. If you don't assume it, you have an argument for it.
Yeah.
If you want to violate gauge symmetries, you better have an argument. He's fine.
I think that
it's not just because we are talking about quantum families that we should give up everything, right?
Exactly.
No, but it's not that the reasoning. But wait a second. Here we are. I mean, I was surprised that you can be so sharp and make some prediction. It seems to me that
you just want to conserve the charges, and by matching the charge of what came in, had to come out.
Right, but
and then you go just go through the options.
I think that if black holes form, as I said, once in a blue moon, you will get a big black hole. And a big black hole will behave like that. Okay. Then, if you see something like this, then you
see so many of the others before you see any of them.
The others will be buried in the junk.
That's not true. You can have an E plus, E minus back to back with 500 check each. That you would see.
Yeah, but how many?
You will have plenty of those.
Any of the other models. There are thousands of models that will give you that signature.
Give me a model and signature.
Let's give the others a chance to ask also.
Yeah, I have a question coming back to angular momentum. I mean, we have heard that the angular momentum is small, but what does small mean in geometric units? I mean, are we expecting most black holes to be created close to extreme?
So we studied the distribution of angular momentum in black holes, and there are very few black holes that are created near extremality. So they are usually created with a j over m, which is small.
But that does indeed mean very little angular momentum.
Yes.
Is there an idea where the angular momentum goes to? I mean, why is it so effectively
it's
taken away?
Yeah, it's because most of these you get a very high angular momentum since these collisions, the impact parameter is close to the maximum allowed Schwarzschild radius, so if these particles are grazing. But most of the collisions, they happen when the particles are close to being head-on. I think that was my understanding. And so you get a low angular momentum. Nevertheless, you have angular momentum, so that should be included. It's just that we don't know how to do it for all fields.
One more, I hope, short question.
Yeah, so one hypothesis as to the quantum structure of black hole horizons comes from group quantum gravity, where the area of the horizon, and this has not been developed in detail for higher dimensional black holes, but still should hold. The area, the spectrum of the area of the horizon has a certain discrete spectrum, which means the mass has a certain discrete spectrum. And when this has been worked out in detail, for example, by Mohammed Ansari, one sees an enhancement of a few lines over the thermal spectrum. If this were the case for the higher dimensional black holes that you're talking about, would you see it? Would you be able to see a thermal enhancement, an enhancement of a few lines over the thermal spectrum?
I don't know if I will be able to see it from the experimental point of view because, as I said, these events are very messy. So even if you change the parameters or if you introduce a minimum length or so on, the effects after you reconstruct the events are minimal because there are so many other systematics and in the event. It might be possible. And that's actually something that it should be done. I mean, check this evaporation in steps and see if you get some effects. That's something worth looking at.
It's been done for the 3 + 1 dimensional black holes.
Yeah.
Not carry through completely.
Right. There is a reason.
The depth reaction is you only need 5 to 6 particles. So between the emission of the particles, the remnant that remains usually gets a lot of depth reaction. So it washes out any delta function like that.
Can I just ask a quick question?
So we have to continue. Better we ask this
Really
question.
quick. So you said that the gray body factors for rotating black holes are not known.
For spin 2 fields in higher dimensions, they are not known. For rotating the
And you need the high dimensional.
Well, these are d-dimensional black holes. So spin 0, 1/2, and 1, they are known in any dimension, but not for gravitons, which is the most important one. There where you expect.
Okay, let's thank the speaker again.